All right, so we are going to go over today, guys, gravitational fields, and this is effectively the last thing in this unit. Okay, so gravitational field strength is what we would call acceleration due to gravity. Okay, they're the same thing. Gravitational field strength measures the rate at which you are attracted to the other object. Okay, whereas gravitational force is the force pulling the two of you together mutually. Okay, gravitational field strength is the rate at which you move towards each other. Right, so they're slightly different. That said, the formulas are very similar, so it's easy to get them confused. Okay, so gravity is a field. We haven't talked about fields yet, and fields are really important in physics 30. In fact, there's a whole unit on forces and fields where you go over why that stupid magnet thing in that movie would not work. Okay, so magnetic fields, electric fields. Okay, but the first field that we go over is gravity. Okay, and a gravitational field, okay, is something that's talked about lots in science fiction. Okay, and it is simply the area over which a body has influence, gravitational influence. It's sometimes visualized by like putting a bowling ball on a trampoline. Okay, and the bowling ball pulls the trampoline down, and anything on the trampoline that's smaller falls into it. Okay, so a gravitational field is sometimes looks like a gravity well or an indent in space, okay, where everything would fall into it. All right, the bigger something is, the bigger the indent in the trampoline becomes, and the more things would be attracted to it. Sort of make sense? Okay. All right, so the idea of a field has been around for quite a while, but it was more discovered with magnets and electricity than it was with gravity. Okay? So like Faraday, for example, who was mentioned in Science 10 briefly, okay, discovered that if you put a magnet down and then you put metallic things around it, they'll orient themselves to take the shape of that magnet's field. Okay? Some of them, they'll all be attracted to it, some will move right towards it. Okay? But if you put a bar magnet on a table, let's say, okay, so like this, okay, with this being the north and this being the south end of the magnet, and then you just throw a bunch of iron filings on it, okay, or around it, you'll get, okay, these lines of magnetic field force forming around it, and all of the iron filings will align to this shape. Okay, now they're not in physical contact with the magnet, so it's not a contact force like all the other forces we've dealt with thus far in this unit, or sorry, in this course. Okay, like friction is a contact force. Okay, tension is a contact force. All of those things require the two objects to actually be touching or somehow connected. Okay, a field force doesn't require that. Right? It only has an area over which the force is exerted. Okay, without contact, and you can see that with magnets. You can see it with electricity and with gravity. Okay, it's the Earth's magnetic field because we have an iron core, okay, that protects us from the sun. Okay, and you can actually see when if there's a big prominence like a solar kind of explosion, okay, and the stuff comes towards us, we can actually see it hit the magnetic field. It almost looks like a shield in science fiction. Okay, and it kind of glows, and the stuff all gets deflected, and we get lots of northern lights when that happens. Okay, that's all evidence that the Earth's magnetic field is working. So gravity is also a field force, and the strength of the gravitational field is directly related to the mass that is generating it, and inversely exponentially related to how far apart they are. Okay? So it works just like the force of gravity because obviously they're related. Okay. So the Earth obviously has a gravitational field. Does the moon have a gravitational field? Do they overlap? What do you think? Do we feel the moon's gravity on Earth? Well, we don't feel it per se, but do we see its effect? Yeah, right? That's what causes the tides, the fact that the moon's gravitational field actually overlaps the Earth's. Okay? So they're kind of competing with each other. Obviously, the Earth's is greater because of the Earth's greater mass. Okay? But there is that overlap, okay, forces acting at a distance. When gravity was first thought of as an idea, it was this whole idea that there were these invisible strings that were holding everything together and pulling on things because they needed some kind of connection, not understanding that some forces could be fields until Faraday came along. All right, so we've got these two things have, okay, their forces acting on each other, okay, but they also have their areas of influence. Now, if I wrote that on the board, you would say, yeah, duh, right? Of course the force of gravity equals the force of gravity. It's like saying 1 equals 1. Yep, it does. Do we have two different formulas for that? Okay, we got this formula, and we got this formula. Okay, they're equal, right? If I'm standing on the Earth's surface and I go m times g, and I go g times m1 times m2 over r squared, and I use the radius of the Earth, I should get the same number, yes? Realistically, I should, okay? But I got an m on both sides. So if I'm going to say that this is the mass of the Earth, what's this mass? Right, this is the mass of the smaller object. So what happens to the mass of the smaller object? It cancels because it's on both sides. There's your formula for gravitational field strength. Okay? We can certainly do this and say, yep, Fg over m, but that's what we just did. We manipulated this and brought m over, and m canceled. Okay? So if I want to calculate the acceleration due to gravity, or gravitational field strength, at any location due to a certain object, I can find that with that formula. Okay? I could figure out what the gravitational field strength would be at the top of Mount Everest, at the equator, okay? Anywhere on Earth if I wanted to. Okay? As long as I've got the mass of the Earth and how far from its center I am, I can calculate the gravitational acceleration. Okay? That formula is on your formula sheet. But here's the thing I'm going to caution you about. You might want to write it down. This is not the same as this. Okay? Gravitational field strength is not the same thing as force of gravity. Okay? I set those two things equal to each other, but because one of the masses canceled, I'm no longer finding the force, I'm finding the acceleration. Okay? And so we really have to understand that those are two different things, because here's what happens every year on the unit exam, even though I warn people with this exact warning. If I make a question and it says, calculate the gravitational field strength, and I italicize, underline, and boldface gravitational field strength of a person, of a 75 kilogram person on Earth at this point, 1/3 of people will do this. Is that gravitational field strength, or is that force of gravity? It's force of gravity. Okay? Gravitational field strength is acceleration due to gravity. Okay? So we have to make sure that we read a question carefully, because it's a super easy question. I'll tell you that right now. It's a super easy question. But people get it wrong because they go to this instead of that. Okay? So make sure you understand that gravitational field strength is acceleration due to gravity, and it's different than force.
Are the units still meters per second squared? Or?
Yep. They can also be newtons per kilogram, because it's the same thing. Okay? When I did this manipulation here, right, I have force in newtons divided by mass in kilograms, right? So newtons per kilogram is also a unit for gravitational field strength, but remember, a newton is a kilogram meter per second squared. Well, if I divide that by kilograms, what am I left with? Meters per second squared. So either one is acceptable. If you ever see, this gravitational field strength and it's in newtons per kilogram, know that that's the same as meters per second squared because of the fundamental units of a newton. Okay. All right. Okay, so like we were saying, Michael Faraday invented the concept of the field to explain how magnets can attract objects. Okay, and later the field concept was applied to gravity. Okay? Anything that has mass is surrounded by a gravitational field, including yourself. Okay? You have a gravitational field, it's just incredibly puny, right? And wouldn't attract anything towards you because it's just too small. Okay? It is the field that acts on the second body. Okay? Remember, the force is mutual. Right? If there's two bodies, they have a mutually attractive force between them. But one is going to accelerate, okay? And it will look like it's accelerating towards the larger one, the smaller one. Okay, we'll accelerate toward the larger one. That's what we're calculating when we calculate the gravitational field strength. Okay? It's the acceleration towards the larger body. All right. So if we're looking at the gravitational field of a single object, this is what it would look like. Okay? That object would have equal lines, okay, of attraction towards its what? Towards its center. And as you get further away, what happens to the size of that field strength? It becomes less. Its direction is always the same, it's towards the center. All right? But it will get exponentially less as you get further away because of the way this formula works. And remember, we said that once you do that manipulation, you've got big G times the large mass over R squared. Okay, so our gravitational field strength is going to decrease exponentially with distance. Okay? Now, what would happen if you had two gravitational fields overlapping? Would this diagram change? So if I put another mass, so here's the center of the first mass. If I was to put another mass right here, even if it was smaller, okay, would it have a gravitational field? Okay, and any areas where they overlap, would that alter what those arrows look like? Yeah, it certainly would. Okay, so it would end up looking something like this. So this could be, for example, the Earth and the Moon. All right, and we can see that between the Earth and the Moon, the arrows are skewed. Okay? So would plotting how to get a spacecraft from Earth to the Moon be a little more difficult than maybe we imagine? Okay? Because you've got to consider that as long as the spacecraft is here, okay, it's accelerating towards the Earth, but you're going to get to a point where they cancel each other out. And once you pass that point, you're now accelerating towards the other thing. Okay, or gravity is trying to accelerate you that way. What should you probably do with your engines at that point? Yeah, I'd turn them off, or you're probably looking at having to turn them around to fire them the opposite direction in order to start slowing down. Okay, one of the big problems with landing on the moon or even orbiting the moon is going slow enough to be captured by the moon's gravity instead of just flying off. Remember, the moon's gravity is 1/6 of Earth's, right? And so you have to be worried about making sure you get that right. If you don't, you could just fly off into space and have no way to get back. Okay? So there are these areas of overlap. Now, of course, we don't shoot a rocket straight at the moon either. Okay? We actually, because the moon is moving, okay, we actually have to aim for where the moon will be when we get there, which means we're going to be crossing some of these areas where the lines are angled, okay, and that's going to change the forces acting on the spacecraft, okay, and require fairly advanced calculations in order to make sure that the spacecraft stays on course. Okay, everybody okay with how that works? All right, so if we're looking at the Earth's gravitational field, like we said, it's kind of similar to the other diagrams, except more colorful. Okay, we got, if we're close to the Earth, our acceleration towards it, our gravitational field strength will be fairly large. Okay, if we're further away from it, our gravitational field strength will be fairly small, but it'll always be directed towards the center of the Earth. Okay. All right, so we're going to look at a couple of examples. There's nothing difficult about gravitational field strength. In fact, it's probably one of the easier concepts in this whole unit. Okay, so it won't take us very long to get through it. Okay, so let's calculate the magnitude of the gravitational acceleration of an object at the equator on the surface of Earth and the moon, but we won't use their numbers, okay, for this one. All right, so if I want to calculate gravitational field strength, okay, I just go big G times the mass of the Earth over R squared, where R will be the radius of the Earth. Okay, so I'd have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 6.37 times 10 to the 6 squared. Now, what do you suppose the most common mistake is with this question? Forgetting to square it. Should you know right away you forgot to square it?
Yes.
Yeah, when your answer comes out to crush people, instead of being around the value it should be for Earth. You'd be surprised how often I see that on a unit exam. Somebody writes in there that the acceleration due to gravity is like 5.9 times 10 to the 2. Okay? No, I think not. Okay? So always make sure your answer makes sense, because if it doesn't, it's probably something simple, like that. Let's start my calculator. Okay, I get 9.83. Why do I get 9.83 and not 9.81? It's actually less at the equator. But that is the average Earth radius, not the equatorial Earth radius. Okay, if you look at your sheet on the back there, it says average Earth radius, not equatorial Earth radius. Okay, the 9.81 is also the average acceleration due to gravity. Okay. So we get that number. Now, the other part of this is, are these numbers exact? And they probably have a lot of numbers after them. Okay, and I didn't include those, and they're two fairly large powers of 10. So not including them is probably a big deal, and probably why we're getting just a little bit off of the number that we should get, 9.81. Okay? All right, everybody okay with how that formula works? Okay, fairly easy to manipulate. Yeah, and you're never gonna have to put like period in there or do that substitution with it. You're basically just gonna use it by itself. Okay, so it's a pretty easy formula to use. All right, let's see if we can do that for the moon. Okay, if we want to calculate G on the moon, okay, then we would need big G, the mass of the moon, and the radius of the moon squared. So we would have 6.67 times 10 to the minus 11 times 7.36 times 10 to the 22, 3.85 times 10 to the 8. No, 1.774. Times 10 to the 6, sorry. That's 3.85 is the distance from the Earth to the Moon. These numbers confused. Okay, so there we go. Those are the numbers for the moon, okay? And we should get a considerably smaller number, yes? Okay. Oh, 7.4. Okay, that number's pretty much dead on, okay? 1.6 meters per second squared for the acceleration due to gravity on the moon. Okay, or 1.76 newtons per kilogram, also accepted. Okay. All right, so just the only trick really with gravitational field strength is remembering to actually solve for gravitational field strength and not force of gravity, okay? The most common mistake. Second most common mistake, forgetting to square the radius, okay? But that one should be obvious when you do it, all right? Okay. Okay, let's have you guys try 1 and let's try 1 and 2 for now. Okay, those numbers are going to be a little bit off because you're going to use the numbers from your sheet. So if you're close, you did it right. Okay, but just note that those numbers are going to be slightly off from what you get because our numbers are slightly different. Okay, so with number 1 here, it says that the satellite orbits the Earth at a distance of 3 Earth radii above the Earth's surface. So part A, how many radii from the Earth's center? 4. Okay, so we got to remember that because we got to multiply 6.37 times 10 to the 6 by 4. Okay, what's the magnitude of the gravitational acceleration of the satellite? So little g equals big G times the mass of the Earth over r squared. Okay, and right away we want to get the radius of the Earth times 4. So 6.37 E6 times 4. All right, so that's the radius number that we're going to use, 2.548 times 10 to the 7. All right. So we'll have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, mass of the Earth, okay, divided by that 2.548 times 10 to the 7 squared. Okay, so we're punching that in here. 6.67 E negative 11. Okay, 5.98 E 24 divided by that number squared. Okay, so we get 0.614 newtons per kilogram or meters per second squared either way.
The textbook says 6.1.
Is it what?
The textbook says 6.1.
Yeah, but that's because they have a slightly different number. Like they have a different radius of the Earth, they have a different mass. They have 5.97 for the mass of the Earth and 6.38 for the radius. So it makes it go the other way, big, right? Because it's a smaller Earth and a bigger radius. Yeah. Okay, how are we doing on number 2? How many people have done number 2? Okay, do we want to go over that one or are we good with that one? If you want to go over it, it's fine, just ask. Okay, then we'll skip that one. Okay, so the big trick with that one was obviously it gave you in kilometers. Okay, now, try number 3. With number 3, what's the trick? What does it ask you for? Force of gravity. Gives you 2 gravitational field strength questions and then throws a wrench. Okay, and says calculate the force of gravity. Okay, that means calculate Fg at that point. Big G times the mass of the Earth times the mass of the astronaut over r squared. Okay, where this time r is 6.6 times the Earth's radius. Okay, and that means then that this number is actually important. Had this question said calculate the gravitational field strength, would that number have been important? Would it have affected your significant digits then? Not if it's not important, not if you don't use it. Okay, it's a pretty common trick. If I give this question on a quiz, a lot of people get it wrong simply because they find gravitational field strength instead of force of gravity. And they use that as part of, or they do a gravitational field strength calculation and include that. Or they use that as the mass in the gravitational field strength question and get an incredibly small number and leave it there. Okay, so if we're doing this one, it's just 6.67 times 10 to the minus 11 times 70 times 5.98 times 10 to the 24, and divided by whatever 6.6 times the Earth's radius is. Okay, so okay, so the gravitational force on that person at that distance would be So that would be our measured value, 6.6. So we would have two significant digits, okay, and it would be 16 newtons on that one. Okay, everybody all right with that? Okay. All right, so little things to watch for, right? Like there's no math tricks, there's wording tricks. It's all wording tricks. We just have to be on the lookout for those wording tricks. Okay. Okay, here's a question I love to put in a multiple choice question. Okay, what is the mass of a 60 kilogram student on Mars and on Earth?
60.
Right. You'd be surprised how on a test people get anxious and they go ahead and they calculate the weight. Okay? Or they're coming up to me, Mr. Coder, I don't know what little g is on Mars, or I don't know what the radius of Mars and the mass of Mars are, and I'm like, you're right, you don't. And they look at me and I'm like, if you don't have them, you probably don't need them. And then they're just more frustrated. Okay? But mass never changes, does it? No. But boy, does that one slip past the goalie often. Okay? Gotta watch out for that one because it's an easy trick. Okay, for me to play on a test. Now, what's the student weight? Well, then you'd need all those numbers, okay, and you could do the calculations. But weight would mean, am I calculating field strength or force? Force. Weight is force. Okay, so just be on the lookout. Again, it's all word tricks. Okay, there's no math tricks here. It's all word tricks. Okay. Okay, I would like you guys to try the ones on, or from the digital workbook here, just to finish things off. So I'll put them up on the board. Okay, and then we did like 6 of them or something. Actually, you know what? Before we do those, I've got 2 questions I want us to do first. Okay, let's see what we remember from last week on satellites. Okay. Just to make your life easier, 7.5 years is 2.36682 times 10 to the 8 seconds. Okay, so at what height above the surface? What are we going to have to do here?
Find the radius.
Find the radius and then what?
Minus the center.
Right, minus the radius of the Earth
Right.
from that distance so that we get just the height or altitude or above the surface distance. Okay, now we got a 12.4 hour orbital period. So first off, we know we're looking for radius, but we're also going to have to find the height. Okay, and we know that the orbital period is 12.5 hours, which we have to convert to seconds by multiplying by 3600. So 12.5 times 3600, okay, will get me the orbital period of 45,000 seconds. All right, so I've got that. I know it's around Earth, so I know the mass of the Earth, 5.98 times 10 to the 24, okay, and that should be all I need. So, because it's a satellite, we know that gravity is providing the centripetal force. Okay, we can start out with mv squared over r, but we know we're going to have to substitute in here for this one. So this will be mass of the Earth, m over r squared. Okay, so we can right away cancel the mass of the satellite, which is important because it was never given anyway. Then we're going to have to plug this in for v, but all squared. So we're just going to erase, okay, all that stuff we have there on the top and plug all of this in. In fact, we're also going to get rid of this r because it's going to cancel. So we'll have 4 pi squared times r over t squared, because that r was squared, but it canceled the r that was on the bottom, and the m is already gone. All right, now that we have that, now we can calculate the radius. So we're going to take r squared and bring it over here. What's r squared times r?
R cubed.
R cubed. All right, and then I'm going to bring t squared over here. Get rid of it on this side. And then I'm going to bring big G times the mass of the Earth over to this side. So now t squared is left on the other side by itself. And then I'm going to square root in order to get t. So I'm going to have the square root of 4 pi squared. Why did I just do that? Why would I find period when I'm supposed to find r?
Yeah.
Is that your point?
Yeah, I was going to say.
Coder, it feels like Monday even though it's Tuesday? Yeah. Okay. Let's just start that over again. Actually, let's not. We have an undo button that's gonna come in really handy right now. Okay, there we go. Now we're gonna solve for r. Coffee, come on, coffee. Okay, 4 pi squared. Okay, and then I'm going to cube root that instead. Okay, first time I think we've cube root on a satellite question. All right, so r is going to equal, in brackets here, or sorry, under the square root sign, sorry, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 45,000 squared divided by 4 pi squared. All right, so that'll give us the radius, which is not our final answer. Okay, so there is our complete center to center distance, but we only want how far above the surface, so we will take that number and subtract from it the radius of the Earth, 6.37 d6. Whoop. How can we be inside the Earth? Did I mess something up there? Gotta have a look at that again. I obviously messed something up. Oh, 4,500. I missed a 0. Ooh, okay. There we go. That's an easy fix. Better. Now we'll subtract 6.37 times 3. Okay, so we're going to be left with 2.10 times 10 to the, so 10 to the 7. Okay, would be our answer there. Everybody all right with that one? You probably struggled less than I did. How many people have done the second one? Okay, we'll give you some time on the second one then. Is it very, very similar? It is, yeah. It actually has one less step. Okay, so it's basically the same thing. Okay, we're going to have m 4 pi squared times r over t squared on one side, and we're going to have big G times the mass of the sun this time, okay, times the mass of the asteroid, that's on both sides, okay, over r squared. So the manipulation is going to be the same. We're going to have r equals the cube root, okay, of 6.67 times 10 to the minus 11 times 1.99 times 10 to the 30, okay, times the period, which was 2.36682 times 10 to the 8 squared, right, divided by 4 pi squared. Okay, so we should get that it is at a orbital radius of 5.7 times 10 to the 11 or so. Okay? All right, and it would have two significant digits because 7.5 years would be a measured value. Questions on that one? All right, tomorrow we will be working on your assignment on gravitation. On Wednesday, we will do a unit exam review. Okay, Thursday, start unit 4. All right, so we start unit 4 on Thursday, do that again Friday, and your unit exam is Monday.
Next.
Yeah. Okay, so that's what's coming up for you guys. So far on the circular motion assignments, they've been an easy mark because you're doing so well. When the right answers are there, I can mark a lot faster. So if we can just come to an agreement where you get everything right, it makes my marking go a lot faster. So if you guys can just keep doing that, like especially on tests and stuff, it's really handy. So yeah, just keep doing that.